Okay. All right, so more aldehydes, ketones, carbonyl reactions, nucleophilic addition. Any questions or anything at the beginning before we do get started?
No, not so
Okay.
much.
Okay. So yeah, the general, of course, mechanism here is there's going to be some nucleophile, and you'll find that we have different types. It is important to recognize you have poor nukes. The poor nukes tend to go through in acidic conditions, and so the carbonyl up on top is going to attack first, and then this is just going to change. And whoever this nucleophile is, you'll get different answers, right? Like if it's a water group, you're probably going to get a digeminal alcohol, two alcohol groups attached at the carbonyl carbon where it used to be a carbonyl carbon. If we bring in a methanol, one equivalent, this is where the new terms start to come in. And we did a bit of that last time, but it was so brief. So that's kind of where we're going to pick up. I'm not going to go through these ones because I think that you're going to be fine with those ones and we could always swing back around. But I think a good place to kind of start, we did one example here with the geminal diol, and then we moved into sort of like, I think that's just kind of another comparison. This is really the next good place to be, making like a hemi. Since you've now had a couple lectures under your belt, do you want to try and like differentiate between those terms? Is it getting a little bit more familiar, like hemi-ketal, ketal, acetal, hemiacetal, or are those terms still pretty new for you?
They're still pretty new. I haven't had a chance to like memorize them yet
Sure,
either.
sure, sure. Okay, no, that's just good info for me, so I know like, oh yeah, you're a pro at them, then I won't go into it as much. But if they're still like kind of new, then I think it's a great place to jump in.
Okay.
All right. So last time we did one equivalent, and our alcohol group wants to go in there again in terms of the mechanism. We started to bypass that first step just because you'll get really good at this. The O grabs the H on top, and that makes a better carbonyl carbon to attack. You take your poor nucleophile, have that come in and attack. And then you get to this place. I will say that at this point, this is where a lot of students can get really tripped up because you got two O's here. There's just a lot going on. And like we talked about, if you kind of draw it like this, I think it'll help you out if you sort of imagine it's like that cat looking face instead of drawing it all kind of convoluted. And so when we bring in just one equivalent, always remember that because we're in H plus conditions, we're going to bring in like the HSO4 minus or a water group or something to come by, snag one of the H's. How do I know which one? The best way to know to be successful on this, because it will start to get a little trippy in here, because there's a lot of things attached to it. Um, you want to think about who has been there already. That's probably going to be your leaving group at that point. And then who do we bring in that's new? That's probably not going to be your leaving group. So, in
Okay.
this example here, I know to clean up this because it just came in. So it wants to be perfectly cleaned up. And now you have a new OR group plus an OH group. And that's where we start to get these terms called hemis. So when you have just one equivalent coming in, you're going to get to a hemi. If we have two equivalents coming in, we'll lose the term hemi, and then we're just stuck with either ketal or acetal. Now, the term ketal versus acetal all just depends on who we started with. So if you start with the K over here, then you're going to end with the K over here. So if you start with the ketone, it's either going to be a hemiketal or a ketal. Okay, and then this one, of course, is a hemi because we're only bringing one equivalent. The next problem we'll bring in two equivalents, and then we'll see we get the full name. Ketal and the mechanism is just barely different, but it is different. It's more steps.
Acetyl come from aldehydes?
Acetal comes from aldehyde. So if you start with an aldehyde, then you can end with either an acetal or a hemiacetal. Just depends on the number of equivalents. Now, making sure we're differentiating who our nucleophile is. If it's a water group, we can't make those terms called ketals or acetals. So if you bring in a water, you're stuck with just the term alcohol or diol or geminal diol. But if we're bringing in an ROH, right, that's bringing an alcohol group plus a carbonyl, you're going to make a new ether over here. So it's kind of like this back in the day used to just be called an ether, but because of where we came from, and now we have this like there's two O's connected to this carbon in the middle, then we get new terms, hemiketal, hemiacetal, etc. Those four new terms. All right, any questions with this before I move on to the acetals and then the comparison of hemis versus non-hemis? Questions?
Nope.
Okay. All right, so same thing, except the magic is just we put a little proton here. Let me make the ink a little bit bigger. So we put a little proton here. This is now not starting with a ketone. We're starting with an aldehyde. Okay, and then we just bring that H all the way down. Follow the H the whole time. You will have a decision where you can continue to draw that blue H. In this case, I will. You technically don't have to at this point in here, but um, I would just be consistent and do one or the other so you don't accidentally add it on one and forget it in another. So this H is following us the whole time. And just like that, we basically get the same answer, except now instead of a hemiketal, we have a hemiacetal. So if you start with an aldehyde, one equivalent, you get to the hemiacetal, and then another way to redraw that just so we get rid of that H because technically it doesn't need to be in there. I mean, you might start to see all kinds of things like the OH could be down here and the OR is up on top, and all of a sudden it doesn't look like that perfect little cat looking structure. So I would just be aware of that because when you have a synthesis problem and you have to work backwards, this doesn't look as obvious as this, you know? So. Okay. So that's Hemi. Basic, same mechanism. I think the non-Hemis get a little bit more challenging. Questions?
Nope.
Okay, perfect. So there's that one. And now I move into the full-on ketal. So the mechanism's a little bit different. Now, as you pay closer attention to the directions, it could say two equivalents. Maybe it says excess. Assume all reagents are in excess unless otherwise stated. Okay, so now we know we're dealing with multiple. So we got to follow the mechanism a little bit more closely because it gets a bit different. So first step's the same. O up on top grabs the H, make a better carbonyl in there. And then you're going to bring in another, your first equivalent here. So that's important. And kind of keeping track of your first equivalent, I think, will be helpful because now you're going to have three different O's to deal with. Your carbonyl O and then two equivalents of this guy. So your first equivalent's in there. At this point, it is actually very teacher dependent. I've seen a few different approaches. I'm going to show you the most streamlined one because I think it will benefit you in terms of like speed, and I technically think it's a little bit more advanced. So you could bring an external HSO4 minus here, clean up the job, and make a nice, clean looking hemi ketal for a brief moment. I'm not, that big of a fan on that because it doesn't guide you into, what the next step is. So I'm going to save that HSO4 minus for later. I do know that I need to deal with this guy, but instead, I'm going to deal with two birds with one stone. I'm going to take this O that's adjacent, and I'm going to hit that H. And the reason is because you're going to make a better leaving group on the left, and you're going to clean up the group on the right. So it's like the perfect little combo. So let's draw the next step. So now this is an OH2 plus on the left, a clean OR group on the right, and then we kind of pause there for a second to reevaluate. So this gets cleaned up. That's neutral. And then this is a better leaving group now, which again, like our philosophy said earlier, if it's been there for a while, it's a good indication it's probably going to leave. If you just came into town, you're probably going to stay for a while. All right, so now we're here. The next step is, of course, well, we have another equivalent of ROH. This is our second equivalent of ROH. The most intuitive thing to do is kind of like an SN2 attack where you go in there and then you kick this group out. Now that's pretty reasonable in terms of mechanism. That's not going to be the best step, but if you are predicting a product and you just need to be super quick, that's the best approach to think mentally to get to the right answer as fast as possible. So that comes in, that goes out. But mechanistically, you want to take the O that's attached to the carbonyl carbon where it used to be, and you want to bring one of these guys downtown and form a double bond. So it's kind of like forming a carbonyl again. And since we're in kind of carbonyl land dealing with aldehydes and ketones, I think it's a good thing to think about because it will help guide you. So you ideally want to memorize the fewest amount of things as possible. So if you can have a mechanism step that leads you in the right direction for the next step and sets you up well, I think that's for the best. So now this comes back down to a carbonyl. This is an OR with the positive group. We lost our group here. I think it's important to follow that guy. That's actually an H2O, so there we go. Probably get an extra point for that. And then we kind of pause here again. So as this came down, you can see that it induced the leaving group to leave. Now, the reason why we did that, and there's a couple different approaches you could take here. You could say, hey, this thing leaves on its own. It leaves behind a carbocation. That's very deficient. So then resonance will explain that this guy can come down. And there's just such long steps, and I don't want to waste your time, right? But theoretically you could have done that, and maybe your professor does that in his notes. So this comes down, and now you have a carbonyl here. And again, it's like the same thing from the very first step, right? We had a carbonyl up on top with the protonated, hydrogen attached to the O. That charged up this carbon so that your new group can come in and hit there. So now your second equivalent of ROH comes in. There it goes. So that's equivalent number 2. Now you're stuck with an OR on one side and an OR on the other. And we're just cleaning that guy up. So now we can bring in our HSO4 minus to finish the job, which is perfect because now you have your double OR. And when you have double, then I'm thinking it's not hemi anymore. It's not cut in half. It's the full blown either ketal or acetal. Same principles. If you started with the ketone, you're going to end with the term that starts with a K. So if you started with a ketone, you're going to end with a ketal. And now they won't ever say full ketal. They're just going to say hemi or it's a ketal. Okay, and then that regenerated the H2SO4, so that's good. And then let's copy all of this. Let's get rid of that. And then we're just gonna copy and paste because it's the same exact mechanism now for the acetal. So if we started with an aldehyde, all we do is follow that H the whole time. Aldehyde H, aldehyde H. You don't have to draw it there, but we are going to draw it since there's a line there. Same mechanism. This comes down. Carbonyl. You can see that's an aldehyde for a quick second there, kind
Mm-hmm.
of. And then aldehyde goes away again, which means that the H is gone. So that's why, like, I think it's okay if you wanted to kind of follow this H for a while, because if you don't, a lot of students will forget to draw it in here, and they'll either do something that looks like that, which looks kind of weird, like it's missing
Mm-hmm.
something for sure, or students will do this and they'll forget to draw on the H, they'll draw on the bond, and then at that point you're carrying a methyl group with you, and then that methyl ends up sticking around for the final answer, and then you will lose points like that. They're obviously very picky. So if you want at the beginning, I would just follow that H for a while. Follow it, and then here again, followed it. And then instead of a ketal, it is a acetal. And then to redraw it, I would just could do really anything, but sometimes I like to not have the H in there. And so it could look like this, whatever you would like. Again, at that point, the final answer is what it is. You don't have to make it look pretty. You got all the right connections here. So full on acetal, because we started with an aldehyde, versus the full on ketal, because we started with the ketone. Okay. So that's the long story short of it. Any questions between those two?
No, I feel like that's a pretty straightforward mechanism.
Good.
Because I think mentally for me, it makes most sense to follow like the positive sign.
Yeah. Hmm.
You know
Yep.
what I mean? Like wherever the positive is, that's where the action's happening, and don't consider the other one.
Yep. Perfect. Sorry. Now, the only way this gets hard, and again, I like to layer things, so I'm not going to layer it right now, but just to put it on your radar, because you can think about it and maybe come up with your own problem. You're just like sitting, on a whiteboard. And there can be intramolecular rings that can form in these mechanisms. So just keep that in mind. So these seem pretty straightforward, right? But then all of a sudden you're given like a pretty hard question and you miss it because it formed a ring. And you're like, how the heck was I supposed to know it formed a ring? So
Right.
that'll be the next thing. But just think about that and how that might form a ring. Okay. I'll try and give you an example. I don't want to give it to you right now because it's not necessary. It's like diving too much into the weeds on one problem instead of like there's a lot more still ahead, you know? So if we have time, which I'm sure we will, but we'll do it later. All right. Any other questions?
Nope.
Perfect. So the next thing is doing this, but with a nitrogen group. So, and we could also do this with a sulfur, but the sulfur one is so similar to the oxygen that I don't want to do it first. We can always swing back around and do the sulfur, but it's like literally the same thing as the O. So I want to do it with nitrogen because the mechanism and the functional groups you make are different. So same thing. We start with the double bond O. Maybe if you can help me solve this one, you don't have to go all the way. You don't have to screen share, but let me just get the problem here, and then you can kind of walk me through some of the steps because they're really similar, but it is nice. It's a completely different functional group. So we're sort of in a different land. Okay. So this is kind of what we're starting with. Again, we have a ketone or an aldehyde, and then on the right, we're still in acidic conditions, but now we have a new nucleophile. So you want to try and talk me through some of the steps?
So acidic conditions, and we have a new nucleophile.
Mm-hmm.
Alrighty, well, nucleophile addition, we know the first thing that's going to happen is the O is going to grab the H from the H2SO4.
Perfect. Yeah, that's good. And then right there, if you wanted to, you could do the resonance step again. We're not today, but if you had to do a full complete mechanism and you wanted to gain an extra point or two, I think you probably would if you're doing a mechanism. So just FYI. Unless your professor doesn't care about resonance, but I see that pretty often. Okay, we
All
got
right,
that. Now what?
so then we're going to have the NH2 attack the positive carbon,
Yeah, good.
and then that's going to give us something, and then we're going to have the electrons push up too. So then we have a neutral OH,
Good.
and then we have an NH3 plus.
Good. And I always prepare myself for the next step, knowing like, okay, if I write NH3, then how am I going to show the grader in the next mechanism step that like this will get hit and then that will, you know what I'm saying? So I always write my NH3 like this, just so maybe you can do that too.
Do we have one or two equivalents of NH3?
Good question. Um, when we're dealing with the nitrogens, it's only going to be one equivalent. So even if you get to like the directions and it says, possibly consider everything's in excess unless otherwise stated, for the most part with these nitrogens, we're never making like di-nitrogen compounds. I haven't seen that. I've tutored this for a number of different courses, different schools too. So for this, we're making really specific types of functional groups. And you'll see that when we get to the end. But for now, just kind of think it's one equivalent.
Okay.
Yeah.
So then if it's only one equivalent, we're not going to have NH3 come in again, but we
Correct.
do have the HSO4 minus lingering.
Mm-hmm.
So
Mm-hmm.
would it just come re-grab that H?
Yeah, no, that's definitely a good point. The HSO4 minus for sure could come in at that point. And again, like mechanistically, I can't say for sure the professor's style. So that's something that for sure can happen. Okay. And if you wanted to do that, I think that's more than reasonable. I'm just going to show you like what I think is like the one extra step above.
Okay.
And we're going to use the O next door to actually help clean up the job to the right.
Oh,
Okay.
and then the water pops off.
Yeah, exactly. So if you're kind of catching on this trend, for the most part, we actually want to ditch that OH group that's there. The only time that we kept it and we were like, didn't think to use that O as a potential nucleophile to become a better leaving group was with just the geminal diol. That's like such a rare example as it is to just get H2O one equivalent. Like you're more likely going to see all of these different variations with hemiketals, ketals, acetals, nitrogens. So, I would say the general rule of thumb is you could kind of think of this guy as, I don't want this to be here. Let's try and get rid of it. So this is our leaving group, but it's not a good leaving group right now. So we reach over, grab the H, make a better leaving group, and then it makes that nitrogen feel more neutral. So now nitrogen has a lone pair, and then we have OH2 plus. Okay. What do you think? OH2 plus.
Well, if that pops off, it's gonna leave an area like that pops off and the electrons go back to the carbon, so the carbon becomes negative, right? So, I mean positive when
Positive,
it
positive. Yeah, good.
so and we don't like a positive, so something has to come back in
Hmm.
or because the lone pair, there's a lone pair on the nitrogen, but I
Yes.
don't think can you form a ring with nitrogen? Like, can you close it that way?
You can, so good point. Let's use the nitrogen because the nitrogen's lone pair can make a double bond, and that's new. You haven't seen this before. So nitrogen with a double bond's pretty new, other than maybe when you were doing like the aromatics and there was like potentially a double bond with the nitrogen and you're doing all that stuff. But this is the first time I think that you're really seeing a double bond, and aside from maybe like a triple bond to a carbon, like a cyanide. So yeah, this end's gonna come down, sort of like force this guy out, and then I always redraw it because when you have the two things up on top, I think that's like really fantastic. Again, if you can think of this as a face, it's gonna super help. But then once there's only one thing on top, I think it's important to kind of straighten things out a bit and put it like right up on top, like as if it were a carbonyl oxygen on top.
Okay.
And the reason for that, the reason why you want to be kind of like mindful of that is because if you can start to get into this idea of like, oh, there's like a double bond here and an electronegative group kind of pulling this way, your brain is already thinking like, oh, okay, I don't know what the next step is, but I know that whatever it is, it's going to want to attack in here, you know, because it's like the same shape. Um, so now we just have to think like, okay, what's going to like possibly go in there? Like, again, let's pause for a second and maybe take a step back. So, first step, oh, grab the H. This all looks good.
Mhm.
Protonated it. Your one equivalent of NH came in. That's great. So at this point, if we had a second equivalent of NH, it would for sure go in there. And that's the mindset. You're like, okay, I'm trying to hunt for like what's going to go and attack in there. Oh, okay, but I only have one equivalent, so I'm not going to actually go in there and attack. Okay, so now we're sort of left with, all right, well, who do we have left then since we only have one equivalent? Just left with the HSO4 minus, right?
Got it.
And so that kind of does the same job that you're probably used to at this point, right? So what's that going to do? Kind of finish up the job here.
So it's just gonna come grab that H, and then we're left with NH at the
Yeah.
top.
Yeah. And that's a super important, you want to really pay attention to that because this will matter depending on how many hydrogens we have with our nitrogen. We can have an NH3, we can have an NH2 with one R group, we can have an NH with two R groups, or we can have an N with three R groups. Every time you add an R group, you have one less H. And so as you do this mechanism, we do it first with what I call kind of like a 0-degree amine, and then we're going to have a primary amine, compare it to a secondary, and then a tertiary, and then a quaternary. You see what I'm saying? So it's like we just bump it up one level at a time, and you'll see every variation possible with a carbonyl and a nitrogen once you do that.
Got it. Okay.
Yeah. But I think generally when this is taught, they may only ever teach a primary and a secondary, and that's it. So I like to do 0 through 4 because if they just teach you 1 and 2, they're gonna test you on 0 and 3, So the best one in my opinion is start with nothing. Okay, great. And we got a nice clean answer. And then do the same mechanism, but now let's have one R group attached to the nitrogen and see how that's different from no R groups attached to the nitrogen. Now, the last thing is the name of this functional group is called, do you know by chance?
I do
That's okay.
not.
That's okay. So this guy is called an imine. Now, the reason why I care about that is because you do need to know these new terms. So imine is a double bond directly to a nitrogen. Now, what's here and here doesn't matter. So when you're on an exam, they could decorate this up as long as they want. They could put a ring next door. It could be a benzene. Like none of that stuff matters. Okay. And again, this could be an H. This could be an H too. So you could start with a carbonyl, with an aldehyde, ketone, or formaldehyde. Doesn't matter.
Okay.
All right. So now we made the imine. That was 0 degrees. Now let's do primary. So I'm going to put basically the same exact mechanism here. Let's just add one carbon and see if anything changes. So we have now, instead of NH3, we're going to have NH2 with one carbon. I'm a big fan of actually just putting a carbon in there. It doesn't have to be a CH3, but like I remember you making a comment a few sessions back where it's sort of like, the professors always do that with the R, but at some point it's like, no, just show me an example. Like, let's do it, instead of just putting R. So look, there's a CH3 there. It's connected to the nitrogen. We got a lone pair and H2. Okay, let's go for it. So
Okay.
same
So the
mechanism, right? Yeah, go ahead.
so the first step is still the same. We're gonna grab the H,
Yeah,
and then it's gonna attack. And now we have the NH with one H coming off of it.
yeah.
And then the oxygen is still gonna go and grab it, right? So then instead of NH2, we're left with NH.
Yeah, good.
Okay, so then that mechanism is still the same. The water leaves. And then when the water leaves in the lone pair, because there's two lone pairs now, right?
There was one lone pair, and now there's no lone pairs, right? We brought it down.
Oh, we brought it down. Right, right,
Yeah,
right.
yeah.
Okay, so then it's positive and it's the double bonded N with one hydrogen and a positive sign, right?
Yeah, and the methyl, right? Because that's our new CH3 group that we're kind of tagging along for
Oh,
the
I didn't
ride
see that
now.
you added another one. Okay,
Yep,
yes.
yep. So that guy's kind of hanging out with us this whole time.
Okay, so then CH3. Okay, so let me go back and add that in. So we have that there and we have that there. Okay.
Mm-hmm.
So then when that happens, can't it just be the same thing where the HSO4 minus grabs the H, but our final answer will have no H. It'll just have N kind of as like an ether.
Yeah, no, for sure. So I think the biggest thing to pay attention to is there's two really important steps. The first super important one is right here, because you see that in order for this OH to do its job, there needs to be at least one H in there, right? Like if this was an NH3 plus, the OH doesn't care, right? Whether there was three H's, two H's, or one H, doesn't matter. Just needs to have at least
Mhm.
one H. So that's an important step to pay attention to as we build the levels from 0 to 4. The next really important step is right here, because again, this HSO4 minus doesn't care if there's one H or if there were two H's, but there needs to be at least one. You see, we're kind of run out of H's though, right? So
Right.
this one worked fine, but you can probably now start to predict as we move along deeper into secondary and tertiary that maybe we're going to start to run into some issues. So those are two very important steps, and we're going to compare and contrast those now as we move on into secondary. So this we started with the primary amine, and then we still end with an imine. So as long as you still have that double bond directly connected to the nitrogen, all good, right? Doesn't matter if this is a carbon or an ethyl, propyl, it doesn't matter what's going on here or here. All right.
Okay.
So now we move on into secondary. So we're going to copy paste that whole thing because we kind of advanced, we progressed, we added a CH3, but now we got to change our reagent again, because so we're gonna have, as we add the R groups, we decrease in the number of H's. So now we're not NH3, we're not NH2, we're NH with 2, and then the R groups can be variable. They don't have to be the same. So I'm gonna do NHCH3, and then I'm gonna do parentheses to say that there are two sets of those CH3s now. And again, it didn't have to be. It could totally be asymmetrical. So nitrogen, don't forget it's got a lone pair, acidic conditions, and then two methyls coming off of it and one H. All right, take it away.
Alrighty, so same first step.
Mm-hmm.
And then when that NHCH3 2 attacks, we have NH. Okay, hold on, let me redraw this. So I'm drawing an N with an H coming off, and then the two methyl groups.
Mm-hmm.
The O is going to swing back and grab it.
Mm-hmm.
And then, so now we're left with an N with two methyl groups.
Mm-hmm.
The lone pair is going to come down. It's going to push out the H2O.
Mm-hmm. And
And now,
now we get to this step, right?
mhm. So now we have double bonded N with two methyls.
Mm-hmm.
Mm-mm-mm-mm.
That's where we run into an issue now. So we just have to decide if this is no reaction or if we can do something that's a little bit clever to still, be able to progress through the problem. So
Well, we have resonance, right? Because we can push the double bond up into the N for the lone pair and create like an area of deficiency and negativity, right?
yeah, totally. Yeah, this can come up and then that
Mhm.
kind of resolves the issue of, well, the nitrogen's positive. I don't really like that. So let's do a resonance structure and compare. Okay, so we do that. Bring up the N, or sorry, bring up the lone pair. Great idea. And then what happens to the carbon?
It's positive.
Yeah, perfect. So that's good. That's a really good observation. This sort of opens up the door to chapter 18 too. Now we're not quite there, but those are the chapters, right? 17 and 18.
Yes.
All the books and chapters is like it's good to know that for the most part, like they just haven't changed the textbook. So yeah, 17 and 18. So chapter 17 in my mind is like ketones, aldehydes, carbonyls, attack the carbon, great. Chapter 18 gets into, okay, yeah, we still have aldehydes, we still have ketones, but now I'm not as paying attention as much into here. I'm actually
Mhm.
caring a little bit more about what's going on just to the right. Because as you probably recall, at some point we've talked about this, but in terms of acidity with a basic carbonyl, which that's like I shouldn't say basic carbonyl, with a carbonyl, right? And that's what this page is, which is kind of cool.
Mhm.
Um, Carbonyls you can either attack in here or you can attack that next door alpha hydrogen because alpha hydrogens are acidic. And the reason is because there's resonance. If I lay down a negative sign here, then I can do a resonance structure, take that lone pair, come downtown here and push this up over there. So with that in mind, that's the approach we're going to take to be able to continue to progress with these amine reactions. So, it was nice while we had the luxury of having an H here and just have HSO4 minus go here, kind of directly solve the issue. But we don't have that luxury anymore, so we have to think a little bit more clever. And we're going to go next door and take a proton. If we go next door and take a proton, then we can kind of accomplish that mechanism idea of, all right, well, next door is still an acidic proton, although I don't have the one that's directly attached. I can go for the one next door, and I can take this HSO4 minus, have it attack here, lay down the double, and then push up the resonance like that. So if you wanted to, you could do the resonance and then draw this structure. That's fine. And then at that point, if you wanted to use this resonance structure, you would go here and then you just lay this down. You don't have to do any more pushing up because we accomplished that in the resonance structure.
Oh, see, I like that better.
Yeah, yeah. So whichever one you like. I
Okay.
personally kind of like this whole domino effect where it's like I'm just getting all my money at once. Like that gets hit, this
Yeah.
gets hit, that goes up. When you're in a crunch and you have, you're on exam, it's pretty tight timing and you don't have to do a resonance structure. I don't want to waste my time doing this.
It can get more
And
complicated.
yeah, yeah, I don't want to do that. I don't want to do that first resonance structure that could come off of here. Like all of that's just unnecessary time. But I think in terms of understanding this, the resonance does help here. And you sort of pointed that out at the beginning, which is great. So we make the double bond next door is the main take home point. So now instead of this kind of looking thing, well, what happened? We pushed up the pi bond and now it's a nice normal single bond. We still got both those R groups. Again, it could be a mixture of things, so they could be asymmetrical up there. And now we're going to lay down our double next door, and you made a new functional group. So it used to be called an imine. Now this is called an enamine. Just like you had enols, right? Like a double bond with um the alcohol, right? Like an enol was something like this, and then the OH. It's the same thing, right? It's like double bond and then the carbon that's connected to the O, that's why we call it an enol. And this is like a double bond and it's connected to the N, so now it's not an enol, but an enamine, right? So here we go. So enamine. So
So
now you
then
have a new group.
where does it matter where we grab the H from? Like if the carbon chains on either side of the double bonded N looked differently, does it matter which one we grab?
Great question. And the answer to that is the more acidic proton that you can find will be the side that you want to attack. So
Okay.
if we go back to like, let me just grab a nice clean carbonyl and then I can answer that. So you want to think about, well, then what causes acidity to go up? And that would be the presence of maybe more carbonyls next door, the presence of an electronegative atom next door, right? So if you kind of get to the point where you're like, okay, I'm going to grab, how do I know to grab that H on the right or maybe the other H on the other side? Well, if this side had, a lot of steric hindrance, maybe I don't want to go to this side, right? Maybe I want to go on this side. Or if we were kind of like this, and I had like, H1 and here's H2, and then there's a methyl group there. So here's H3. That's three different places. Like, so what do I do? Just hit all three of them. I get three different answers, like, draw all answers. Mm, you're going to only get one answer because in this case, the H2 in the middle is connected to a carbonyl on the right and it's connected to a carbonyl on the left. So that's like double the resonance versus this guy's all alone. And this guy has an extra methyl group, which kind of decreases the acidity, makes a little bit more steric hindrance. So hopefully that helps in terms of like if it were asymmetrical in this moment, how do you know like which of those two sides to attack? Use some of those trends to lead you in the right direction.
Okay.
But really good question. Okay. So now you know the difference between an amine, that's just a nitrogen with some H's, a nitrogen with some carbons, nothing fancy. An amide, that's a nitrogen with a double bond O next door. We didn't do that today because that's carboxylic acid reactions when you get to 118C. Um, and then there's imine and enamine. Imines you can make from 0 degrees and primary. The enamine you can only make from secondary. So then that kind of begs the question, well, what about tertiary and quaternary? So you probably know, just because we did a few, that you kind of run into more and more issues as you make that nitrogen a bit bulkier each step of the way.
Mhm.
When it was 0 degrees, you had no issues. When you had primary, you're like, okay, I have to start thinking about things, but I still got the same answer. So that was fine. Secondary is like, holy crap, I ran out of an H over here, right? And I had to think super clever and grab an H from somewhere else. Whew, geez, that was a close one. But now tertiary kind of just busts the ceiling open and we run into issues like straight from the get-go. So you probably remember I told you there's a few places you want to look that are very critical spots to do the problem. So if they ever give you a carbonyl with a tertiary amine, the answer is straight away no reaction. Because when you get to this point in here, there's no H to take. And that H is critical because if you don't have that H, you can't reform the lone pair on the nitrogen, which means you
Mhm.
can't kick out a leaving group. So we're kind of stuck here. This is fully positive. O has no business, no reason to do any kind of funny monkey business because the only reason it would go here is because that's partially positive, We can't do anything here. We're not going to do like an SN2 attack on a primary carbon with a poor nuke?
Right.
So there's nothing we can do there. We're stuck. We can't progress throughout the problem, and you could sort of like run into a dead end right there. So from this point, moving forward, the answer is just no reaction. They're not going to do a mechanism problem for you on this. There's no mechanism to be had.
And that's
And
always, is that the same thing with an aldehyde too?
yes, all of this is applicable for whether it's a ketone or an aldehyde.
Okay.
Now, for quaternary, same story. So, you know, clearly you just run into big time issues once you get into those deeper levels. So, separate this tertiary on the left, quaternary on the right. Now, the quaternary on the right is going to be even worse because you don't even have a lone pair to go in there and attack. So like we're going to lose a lone pair and add another methyl. And again, those don't have to be symmetrical, but now you don't even have a nucleophile. I mean, this thing can't even come into here and do anything. So from the very beginning, you're seeing with tertiaries or quaternaries, big time issues, no reactions. And that means honestly lower yield content, but the chance that one of those sneaks up and is one question, definitely, right? Because you need to know the most commons, which are like zero, primary, secondary.
Mhm.
But then they could throw one of these at you and you accidentally do something and it's supposed to be no reaction. You get no
Yeah, he
no
did
credit.
throw a no reaction in on the exam, so I'm not surprised.
Yeah, there you go. So this would be a good place for that. And I found that when I was a student, um, there's only so many times it happens. It's not like it happens all the time. So when you see one, you're like, oh, okay, let me make a mental note of that because you only ever run across like a no reaction once in a blue moon, maybe one in 10 reactions, maybe. So. Okay, no reactions for those guys. Sweet. So, I mean, hopefully you're seeing the mechanisms are like all very similar. You have a carbonyl, you just attack the center. That's pretty much it. And then you're just on repeat with oxygens, whether it's in a water, oxygens and an alcohol, nitrogens, different levels, or sulfur, which acts basically just like an oxygen. Other than that, you're not going to see any other types of poor nucleophiles coming in. The only other type of nucleophiles attacking your carbonyl carbons are going to be like your reducing agents like an NABH4, a lithium aluminum hydride, LiAlH4. Other than that, that's sort of where chapter 17 ends, and then chapter 18 begins.
Okay. So
All
then
right.
chapter 17 is basically forming aldehydes and ketones from alcohols.
Mm-hmm.
Then we move into like terminal alkynes with BH3, THF still to give you an aldehyde
Mm-hmm.
or H4 to give you a ketone. And then you can um let's see. You can reduce them back to alcohols, but then those look a little bit different depending on what you're reducing with. And then there's nucleophilic addition, right?
Totally. Totally. Yep. 100%.
So
So
that's
in
not
terms, yeah, in terms of the chapter, really it's okay, making the aldehydes and ketones, no problem. It's a bit of review. Then the next big chunk is nucleophilic addition, carbonyl. What are you doing? You're just attacking it. Cool with
Mhm.
different things. Easy, right? That's like I almost want to say all of it.
Yeah.
But there's a third phase to the chapter 17 that's just a bit different.
Mhm.
And I would group that as more of like special reactions. So in
Right.
general, you can group all of the things we just talked about as one big chunk. And that covers like a large amount. And then there's like the last phase, which is just like a couple random reactions that don't really follow like the general pattern, that are a little bit harder, longer mechanisms, more convoluted, lots of points on the line. Um, and so those are going to be like your Wittig, those are going to be like your Wolf Kishner. I don't know if you've heard those terms yet.
He mentioned Wolf Kishner today.
Yeah. So that's the last phase of chapter 17. So once you feel good about like those first two thirds, like, yeah, I can make an aldehyde ketone. Yeah, I can do most of the reactions of aldehydes and ketones. Then you move into kind of like the special reactions. And like I said, Wolff-Kishner, Clemmensen reduction, Wittig, some of the special reactions with sulfur, because like I said, they're very similar to O, but they have something unique that O doesn't have. And that's again, I would group it as like a special. The reason why I want you to do that is because I don't want you to think like, oh crap, I still need to learn five new mechanisms. It's like, well, just bundle all of that up into like special category and be like,
Mhm.
okay, it's like three phases, super easy making them, reactions of the aldehydes and ketones, and then the third phase is just like super special things. And then once you finish that, then you jump into chapter 18 with like the dicarbonyl systems. Now you have two ketones. So you have a mixture. You got a ketone and an aldehyde. What do we do? So I think that's where we're at for the most part. Okay. All right. So that finishes that big phase. Now it's always gonna be honest. It's always kind of I kind of think of it as like a discretion, like what do we want to do next? We could jump into some of the specials. I'm open to that. They just take a little bit long. Um, I don't in the past, I used to just go through the full mechanism. And it's always been fine, but I just got to a point where it's like, look, it just takes too much time. The benefit for just doing one super long mechanism that eats up 20, 25 minutes of a tutor session, it's like, maybe let's not do that, you know?
Mhm.
So
Can we
what I'm
talk
gonna,
about organometallics?
yeah, oh, for sure. Yeah, we could do that.
Love it.
That's no problem. We can do that. So, um, I'm gonna write it down real quick so that you know. So things on our to-do list is still to talk about Wolf Kishner, okay,
Hmm.
and then to talk about Wittig, and then to talk about sulfur.
Okay.
Now, the reason why I'm going to write it down like that is because what I think would be good, especially because the final is looming. I think the best bang for your buck is to accomplish as many big reactions. Like, so you know how for chapter 17, if you learn one system, you kind of can do it on rinse and repeat for all of the different functional groups they throw at you. It's like, okay, I understand the whole process, right? We're not like memorizing things. Um, I want to show you that process for chapter 18 because it is something similar, totally different, but it is something similar where if you can learn a process I can allow you to kind of learn a ton of reactions fast versus if we spend time here, you know, you might get good at Wolf Kishner, but then it's like, all right, there's a lot left, you know.
Hmm.
So what we'll do some chapter 18. I'll do organometallic right now. We'll do chapter 18 and then we'll swing back and we'll do some of those special ones. Because I think, like, let's say you just said, you know, screw it, I'm not going to learn Wittig. That's only one reaction. Versus if we didn't get into chapter 18, that's going to be half the test in terms of chapter 17 and 18, you know?
Hmm.
All right, so let's do organometallic and then we'll squeeze in a little bit of chapter 18 and see what we can do in 7 minutes. All right, but does that sound okay for a plan?
Yes.
Awesome. It's kind of what I've been doing lately. Seems to be better because Wolf Kishner is just such a long mechanism. All right, so organometallic. So for this, it's actually you can kind of group it into the first category where it's like the making double bonds, making ketones and aldehydes, doing like lithium aluminum hydride, ALH4, and a BH4, same idea. But in this case with organometallic, we have RMGX.
Hmm.
So this could be any assortment of R group. Let's say we have a asymmetric group like that with magnesium connected to Br in a diethyl plus H plus. So what I think is the bond in here is going to be very reactive because the Br is pulling. It induces a partial positive character on the magnesium. The partial positive character on the magnesium is so partially positive that it actually makes the carbon feel partially negative. And a partially negative carbon or a full-on negative carbon are great nucleophiles. So then what happens is because magnesium is like a weird metal, magnesium says, hey, look, you can just jump off, go do your thing. I'm not going to add as a final answer, but I helped create a good nucleophile. And now the magnesium's done its job. We don't have to follow it anymore. When that gets uh, attached into the carbonyl carbon, pushes up, you got an O minus up on top and then your new R group. So in this case, if I just follow the bond, I hit one and then two and then three. So same thing, I follow the bond, I hit one, I hit two, and then I hit three, and then I go back and find any extra methyls or substituents. So I hit one and then I hit two. So off of two, there's the methyl. So one and then two and then the methyl and then three. And then the last step is just cleaning it up. And this could be an H plus. It doesn't have to be an H plus. It could be in basic conditions. But generally, usually acidic conditions. And then this hits that. And you make an alcohol group to finish. And it's actually one level above what it used to be. So this was kind of like one carbon on the left, one carbon on the right, sort of like kind of like a secondary thing going on. And then you finish with tertiary because now you added a new R group plus the old R groups that you had. One and then two and then three. If you started with an aldehyde, we only have one carbon. So then when you do RMGX with one equivalent, then you bump up to secondary. If you had a formaldehyde and you had no carbons and you have one equivalent of your Grignard, then this guy comes in, you go from no carbons to the addition of one carbon.
Okay.
So yeah, this can happen with ketones, aldehydes, formaldehydes. And then your Grignard generally looks like this, or organometallic encompasses both Grignard, and then another organometallic is just RLI. So it's the same idea. You have this cool new R group, and it's connected directly to a lithium. And again, same idea. The bond in here is reactive. So this guy just wants to go into there and do the same exact mechanism at that point. So the lithium detaches. We don't ever follow the lithium. It's not part of your final major organic material. We don't follow the magnesium. And then you added your new R group and that's it. And then you clean it up with an H plus, and now you have a new alcohol group plus the R group.
Okay. That makes sense.
Cool.
Hmm. I'm
Other
looking,
questions?
yeah, I'm looking through my lecture
Sure.
notes. Okay, so we did briefly talk about sulfur, but that's next time. Can
Yeah,
we go through quickly the mechanism of reacting a ketone with an HCN?
sure. Yeah. So with the HCN can be tested in two different ways. It can be an HCN or it could be a KCN in H plus.
Okay.
So if we have carbonyl up on top plus HCN, so like this, or KCN, comma, and the H plus can always be H2SO4 or H3O plus. So two different ways that it can show up on the test, but same style of mechanism. So generally, like we said, we love chapter 17 and 18 because for the most part, the first step in the mechanism is always the same. Carbonyl up on top grabs an H. And so in this case, you can grab it from an external H plus if you're down here, or you can get it straight from the HCN. So grab the H and then you make a carbon like that, gain a new lone pair. So now you got carbon, triple bonded, nitrogen. And this is where we make that comparison of like just because you have the same number of lone pairs or more lone pairs or less, like doesn't really matter. It all kind of depends on like, okay, this is a lone pair but neutral. This is a lone pair but negative. So that's a pretty dang good base, you know? So that's kind of how I think of things. So the O up on top grabbed an H. Of course, that made a better electrophile to hit in the center here. So I want to go hit in here. Now what we're used to is generally the nucleophiles are usually neutral, right? In this case, it's full on negative, but it's not like a strong base because you still have that acidity pulling this way from the electronegativity. And remember, as you increase the number of pi bonds, that increases the number of acidity and increases the S character. So it's not that great of a nucleophile or a strong base. So this comes in. I guess it's a good nucleophile, but not a strong base. And then that gets pushed up. And now you have an OH plus the CN group. And they call that cyanohydrin. That's your 1 point vocab style of question. I think for this chapter, you've learned new functional groups. You've learned that this is a cyanohydrin. You've learned that there are imines and there are enamines and ketones and hemiketones and this and that. Like chapter 17 is kind of learning a few new terms, but it's nothing like the new language we had to learn with aromatics. Like that was a lot, you know? I think generally chapter 17 is more straightforward compared to benzenes and dienes and, dienophiles and all that stuff. Takes you back to some more core principles like just a simple SN2 reaction. Like that's pretty nice. But yeah, so that's how this works with the HCN, whether it's HCN or it can be KCN comma acid. And then in that case, you just take the H from the external, H plus conditions, and then your CN comes in and is a little bit patient and then attacks.
Okay.
You get the same answer though. Awesome. All right. So I think that's where we finished off. So I think next time we'll start with chapter 18, and then we'll also do some of the Wolf Kishner uh Wittig sulfur stuff. I was kind of peering through your notes too, and you guys did a little bit of that. The sulfur stuff's not too bad. We can catch that up in easily 5 to 10 minutes. Um, and then like I said, the Wolf Kishner and the Wittig, we'll be able to fit it in when I think is a good time, where it's like maybe we did like 42 minutes of chapter 18, and then we're like, oh, we have 18 minutes left. Great time. Let's knock out one of those. Let's do a Wittig, you know?
Yeah.
Um, or yeah, that'd be good. Okay, questions.
No, I think that's it.
Sweet.
Um,
Um,
can we reschedule the Saturday session or the Sunday session right
for
now?
sure. Yes.